The world of seismology was electrified in March 2025. A powerful 7.7 magnitude earthquake struck Myanmar. This tragic event sadly resulted in approximately 3,700 fatalities. Damage from the quake extended over a wide area, even reaching as far as Bangkok. However, amid the devastation, something truly unprecedented emerged. Surveillance footage captured a phenomenon never before seen with such clarity. This footage has provided an invaluable window into the raw power of our planet. It offers a unique opportunity for scientific advancement in understanding earthquakes. The remarkable video was recorded in Mandalay, Myanmar's second-largest city. It clearly shows the ground surface, including a driveway, visibly rupturing. The land on one side of the rupture can be seen sliding horizontally past the other. This dramatic movement is believed to have occurred along the Sagaing Fault. This fault is a major geological feature in the region, known for its seismic activity. Witnessing this in real time, rather than inferring it after the event, is a profound moment for earthquake science. The clarity and directness of the footage are simply astonishing. This event represents a significant breakthrough in earthquake research. For the very first time, scientists have footage of the Earth's crust visibly tearing apart and sliding during an earthquake. This provides direct, real-time visual evidence of fault dynamics as they happen. Previously, our understanding was built largely on indirect methods. These included satellite imagery taken before and after events, or ground surveys conducted days or weeks later. This new footage changes the game. It allows us to observe the mechanics of an earthquake with an immediacy we never had before. Expert reactions have underscored the immense value of this recording. As an assistant professor at Cornell University, I myself describe the footage as staggering to see a fault slide in real time. It is truly a really striking observation. Often, scientific instruments placed near the epicenter of large earthquakes are disrupted or destroyed. This makes direct, close-up instrumental readings of the rupture process itself very difficult to obtain. Wendy Bohon, a California-based earthquake geologist, called the footage mind-blowing. She noted that it showed the actual complex natural system, far surpassing what computer or laboratory models can currently replicate. Lateral ground movement is a specific type of ground displacement that occurs during some earthquakes. In simple terms, it means the ground moves sideways or horizontally. Imagine standing on one side of a line and the ground on the other side of the line slides past you. This is essentially what happens along a fault during lateral movement. The Earth's surface on one side of the fault shifts horizontally relative to the other side. This kind of motion can cause immense stress on structures built across the fault line. Roads, railways, pipelines, and building foundations can be torn apart. This movement is fundamentally caused by the behavior of tectonic plates. The Earth's outer shell, its crust, is not one solid piece. Instead, it is broken into several large and small segments called tectonic plates. These plates are constantly in slow motion, driven by forces deep within the Earth. Where these plates meet and interact, immense stress can build up over long periods. Faults are fractures or zones of fractures between two blocks of rock. When the accumulated stress along a fault exceeds the strength of the rocks, it releases suddenly. This sudden release of energy is what we experience as an earthquake, causing the ground to shake and shift. There are different ways faults can move, leading to different types of earthquakes and ground displacements. Lateral ground movement is characteristic of what geologists call strike-slip faults. In a strike-slip fault, the blocks of rock on either side of the fault plane move predominantly horizontally. The Sagaing Fault in Myanmar, where the recent footage was captured, is a major right lateral strike-slip fault. This means that if you were to stand on one side of the fault and look across to the other side, that other side would appear to move to your right. This specific type of movement was clearly visible in the remarkable footage. While some earthquakes cause the ground to move vertically, with one block of land rising or dropping relative to another, lateral movement has its own set of severe consequences. The shearing forces involved in horizontal displacement are incredibly powerful. They can create long, visible ruptures on the surface, as seen in Myanmar. This type of movement can also trigger liquefaction in susceptible soils, where the ground temporarily behaves like a liquid. Understanding the specifics of lateral ground movement is critically important for assessing seismic hazards and for designing infrastructure that can better withstand these powerful natural forces. The visual data from Myanmar offers a raw look at these processes. For many years, scientists have diligently studied earthquake-related ground movements using various methods. Global Positioning System, GPS stations, placed strategically, have allowed us to measure the slow, steady creep of tectonic plates and the more sudden displacements that occur during and after earthquakes. Satellite-based techniques such as interferometric synthetic aperture radar, INSAR, compare images taken before and after an earthquake to map ground deformation over wide areas. Seismometers, of course, record the seismic waves generated by earthquakes, providing information about the earthquake's location, magnitude, and the nature of the fault rupture. Post-event field investigations involve geologists meticulously mapping surface ruptures and other ground effects. These traditional methods have provided a wealth of knowledge. However, they also come with certain limitations, particularly when it comes to observing the rupture process itself in real time. GPS measurements, while precise, often provide data points reflecting the final displacement rather than the dynamic process. Satellite imagery offers a before and after snapshot, missing the crucial moments of the rupture unfolding. Seismometers are excellent for detecting shaking, but they don't directly see the ground tearing apart. Furthermore, instruments located very close to a large fault rupture are often damaged or overwhelmed by the intense shaking, leading to incomplete data from the most critical areas. Post-event surveys, by their nature, occur after the fact. The footage from the March 2025 Myanmar earthquake marks a pivotal shift from these indirect observations to direct real-time visualization. We are no longer solely relying on interpreting instrumental data or post-event mapping to understand what happens at the surface. Instead, we can watch the ground itself break and slide. This is akin to moving from reading a description of a phenomenon to seeing a high-definition video of it. As I previously noted, the fact that instruments are often compromised during such intense events makes this visual confirmation incredibly valuable. It fills a critical gap in our observational capabilities, offering ground truth at its most visceral. While exceptionally clear, the Myanmar footage is not entirely alone in offering visual insights. For instance, video footage from the 2018 Sulawesi earthquake in Indonesia also captured dramatic scenes of lateral spreading and the rapid development of large tension cracks in real time. These occurrences, though still rare, consistently demonstrate the immense scientific value of visual data. They allow us to validate our models of fault behavior and soil response. Sometimes they even reveal unexpected complexities that our models had not predicted. The Myanmar video posted on the 2025 Sagaing Earthquake Archive YouTube channel, which hosts over 1,000 videos from the event, is a particularly stark example of this observational power. The availability of real-time footage, such as that from the Myanmar earthquake, has profound implications for earthquake research. It provides an unprecedented opportunity to analyze fault behavior with a level of detail previously unattainable. Scientists can now directly observe the speed of rupture propagation at the surface, the way the ground deforms, and the interaction of the rupture with man-made structures. As earthquake geologist Wendy Bohon highlighted, this footage shows the actual complex natural system, which often behaves in ways more intricate than our simplified computer or laboratory models can fully capture. This raw data allows for a richer, more nuanced understanding of earthquake mechanics. This new kind of data is invaluable for improving our seismic models. These models are sophisticated computer simulations that scientists use to forecast potential earthquake scenarios, including the likely location and magnitude of future events, and the intensity of ground shaking that might result. By incorporating direct observational parameters from the Myanmar footage, such as the velocity of slip and the width of the deformation zone, these models can be refined and calibrated. This leads to more accurate hazard assessments. More accurate assessments, in turn, enable communities in seismically active regions to better understand their specific risks and prepare more effectively for future events. Ultimately, enhanced understanding and improved models translate directly into better disaster preparedness and mitigation strategies. Engineers can use the insights gleaned from such footage to inform the design of more resilient buildings, bridges, pipelines, and other critical infrastructure. For example, understanding the exact nature and extent of lateral ground displacement can lead to improved building codes that mandate specific foundation designs or flexible connections for utilities. This can significantly reduce damage and save lives during future earthquakes. Furthermore, urban planners can use more accurate seismic hazard maps to guide land use decisions, avoiding construction in the most dangerous zones. The 2025 Myanmar earthquake footage, captured by ordinary surveillance systems, underscores the critical importance of continued and expanded monitoring efforts. Investing in widespread, robust monitoring networks, including seismic sensors, GPS stations, and even readily available video recording devices in vulnerable urban areas can yield invaluable data. This specific video, which garnered over 1 million views on YouTube, demonstrates the power of shared information. Future research will undoubtedly build upon these direct observations, leading to further breakthroughs in our quest to understand earthquakes. This knowledge is paramount as we collectively strive to build a safer and more resilient world in the face of these powerful natural hazards.